Okay, so this is this is section 4.4, which is on complex and imaginary numbers. So the way that you would start with number 15 is that you would look for any perfect squares that can be factored out of that. So for example, I'm just going to list the perfect squares right here. These are numbers that we get by multiplying numbers by themselves. So for example, 4 is 2 squared, 9 is 3 squared, 16 is 4 squared, and so on. And the idea is you want to look for the biggest possible perfect square that you could pull out. So obviously 100 does not go into 128, 81 doesn't work, but 64 does work. Okay, this turns out to be, and actually let me first do this. We'll first pull out a -1 because that's a negative square root. And then 128 turns out to be 64 times 2. Okay, this right here, the square root of -1, another name for that is the number I, or the imaginary number. The square root of 64 is equal to 8. And then you can't do anything more with the square root of 2. So the final way to write this simplified version, it's customary to just reverse the order of those. So put the 8 in front, put the I second, and put the square root by itself at the end. So the square root of -128 simplifies to 8I root 2. Alright, number 16, this is just basically combining like terms, so 7 plus 7i. When you have a minus in front of a parentheses, what you do is you remove the parentheses and you kind of distribute that minus to each thing inside. So it looks like that. 7 minus 5, that equals 2, and 7i minus 8i is minus 1i, or minus I. So that's as simple as it gets. Okay, this is a little bit more with imaginary numbers. So for 17, we would FOIL this out. And again, FOIL means first outside, inside, last. So the first terms are -5 times 5, which is -25. The outside terms in that parentheses would be -5 times 20i, which is -20i. The inside terms in that parentheses will be -6i times +5i, which is -30i. And then finally the last terms in that parentheses will be -6i times +4i. -6 times 4 is -24, and I times I equals I squared. So now we can simplify this. By the way, I squared, since I is equal to the square root of -1, I squared, if you square this thing up here, squaring and square rooting, those two things cancel each other out. So that means I squared equals that number. So another way of writing this is -24 times, again, I squared is -1. So this right here, -20 minus 30i is -50i. And then this number right here, that turns out to be 24. So you're going to have -25 plus 24, which is -1. So that would be the simplified answer. Alright, this one right here is a little bit trickier. You have to use something called the conjugate. And the conjugate basically is this bottom part of the fraction, the denominator of the fraction, but you have to change that sign. That's the only thing that changes. So this -7 stays the same, the 8i stays the same, but this becomes a minus. And we'll do that on the top and the bottom. The reason you do that on top and bottom is -7 minus 8i divided by itself, that equals 1, and nothing happens to a number if you multiply it by 1, it just stays the same, so that's why we're allowed to do that. Now we're going to do the same thing as what we did on 17, so we'll FOIL this out. If we do this correctly, the bottom of that fraction, in order to consider this number simplified, the bottom of the fraction, the denominator, shouldn't have any i's in it. And so that's why we use the conjugate. This is going to create what's called a difference of squares, and we'll cancel out the middle term, so let's verify that. So -7 times -7 is 49. That's this one times this one. And we have the outside terms. This is FOIL again. So -7 times -8i is plus 56i. And we have the inside terms. 8i minus 7 is minus 56i. And that's what we want to see. We want to see these two things cancel, which they do. And then finally, the last terms would be 8i minus 8i, which is minus 64i squared. Now we said we're not supposed to have any i's left. And if you recall from the last problem, I squared is actually a number. It's equal to -1. So this whole thing is the same as -64 times 1, which is plus 64. So we'll simplify that bottom in just a second. Then we'll FOIL the top, so 10 times negative 7 is negative 70. The outside terms will be 10 times negative 8i, which is negative 80i. The inside terms turn out to be negative 3i times negative 7, which is plus 21i. And then finally, the last terms are negative 3i times negative 8i, which is plus 24i squared. I squared is the same as negative 1, so this is like 24 times negative 1, or negative 24. Then we can simplify this very last component right here by just cleaning up the top and the bottom. So the bottom turns out to be 49 plus 64, and that's 113. The top turns out to be negative 70 minus 24, which is negative 94. And then this part right here, negative 80i plus 21i, is minus 59i. And you could leave the answer like this, or if you prefer, some people like to split this kind of down the middle into each thing having its own fractions. That would be negative 94 over 113 minus 59i over 113. That's equivalent to the previous one. Doesn't matter which one we use. Alright, this one right here, raising I to enormous power. So really what you need to know here is the fact that there's a pattern that repeats with the i's. And there's a proof for this in one of the earlier videos, but the pattern goes I to the first is I to the second we already said was negative 1. I to the third, that's the same thing as I to the second times I to the first, because we're supposed to add those exponents to get to 3. So I to the second we already know is negative 1, and I to the first is I. Negative 1 times I is negative I. And then I to the fourth, that's the same as I squared times I squared, which is negative 1 times negative 1. That's where the 1 comes from. Okay, so how does that help us? Well, if you kept this pattern going, it's just going to keep repeating itself. So this is like the next 4 right here. So how do you find something like 237,344? That's the one we have to find. What you do is you take this number right here and you divide it by 4. And what's nice is dividing by 4, you really only need to pay attention to those last 2 digits. If 4 goes into the last 2 digits, it goes into the whole number. So 44 divided by 4 equals 11. We don't care about the 11, though. We care about the remainder when we do that division. So when you do 44 divided by 4, you get 11 with no remainder. Well, there's 4 possible remainders here. You could have remainder 1, which is this one. You could have remainder 2 when you divide by 4, which is, that means it's going to behave like I to the second power. You could have remainder 3, like this number right here. And if you do a division and you get remainder 3, it's going to equal I to the 3. Or this last one, if you divide 4 by 4, you'll get remainder 0. So anything that has remainder 0 is going to be this one right here. That's going to be the same thing as I to the fourth, which equals positive 1. Alright, 4.5, completing the square. The pattern for a perfect square is that the last number right here, and by the way, this, just to recall, this is standard form, ax squared plus bx plus c. When you're completing the square, you need that number to be 1, which it is for both of these problems. The pattern is to find this number. I need to take half of this middle number. Half of negative 12 is negative 6, but that's not the answer. We don't want to use negative 6 to find c. To find this number, we take negative 6 and we square it. And negative 6 squared is that right there. It's 36. Same thing right here. We'll take half of 15, and that's 15 over 2. Once again, 15 over 2 is not what c is supposed to equal. C is supposed to equal 15 over 2. The whole thing squared. That's the pattern that all perfect squares follow. 15 over 2 squared is 225 over 4. Okay, now we'll use this to actually solve some equations. So what we want to do here, this is not going to factor number 22, so we want to move this number over so we can get something that we can then complete the square on. So now if we try to complete the square, we'll take half of this number, which is negative 12, and we'll square it. And a lot of people forget to do this. If you do that to the left side, you have to do it to the right side also. So this becomes x squared minus 12x. That number is plus 36. Negative 17 plus, again, that's 36. Negative 17 plus 36 is 19. And then what was the point of that? It was because now x squared minus 12x plus 36, that's now a perfect square. We can now factor this and solve it like we would normally solve a factoring problem. So this turns out to be x minus 6. Where did the minus 6 came from? It came from half of that number right there. And then this is still 19. Right now I can't add 6 to both sides because it's stuck under the squared, so I need to square root this. I need to square root that, and there's always two things you could have squared to get the number, the positive and the negative square root. So these two things, the square root and the squared, cancel each other out. We're left with this right here. And then the final step is to add 6 here and add 6 right here. And that's our answer, 6 plus the square root of 19 and 6 minus the square root of 19. There's two solutions. The last one on 4.5 is a very similar problem. There's one extra step though. We divide that down the middle. Here we can't do very much until this number is equal to 1. That's what we need to complete the square. So let's start by moving the 49 over because that won't factor. So we get 2n squared plus 16n equals negative 49. Again, we need this number to be 1, so that means we have to divide everything by 2. If that were 5n squared, you would divide everything by 5. So when we divide by 2, we end up with n squared plus 16 divided by 2 is 8. And this is still a fraction right here. Okay, now we're at a position where we can complete the square. So we take half of this number, which is 4, and we square it and add it to both sides. Okay, so then this simplifies out to be n squared plus 8n plus 16. And over here we're going to get negative 49 over 2. 4 squared is 16 like we said, but since we have a fraction we're adding it to out of 2, we want to change 16 or 16 over 1 into 32 over 2. So this turns out to be 32 over 2. Okay, then we can factor this right here, so this is a perfect square. It turns out to be n plus 4 squared. Once again, where did the 4 come from? It came from half of that number. Over here, this turns out to be negative 17 over 2. We will square root both sides here, so that's square root and that's square root. This is a positive or negative that we could have got to square that. So squaring and square rooting cancel each other out. We get n plus 4. And then right here, because I have that negative, I want to pull out an I, because I is the square root of negative 1, so we get this right here. We'll subtract the 4 and subtract the 4. And you can leave the answer like this, that's not wrong, but to make it a little bit more simplified, a lot of times what people will do with this right here, this fraction, which is the same as the square root of 17 over 2, you can take that square root and apply it to each part of the fraction. A lot of people do something called rationalizing the denominator, which means whatever this is gets multiplied here and here. And 17 times 2 on the top, that's square root of 34. Root 2 times root 2, that's root 4, which is just 2. So if you wanted to write this a little bit simpler, you could say plus or minus I root 34 over 2. That's the same exact answer. Alright, we'll pause here, and in the next video we will work on these quadratic formula problems that you see right there.